Good afternoon everyone. Thank you for joining me for today's video. I am Mr. Ish. We will continue from where we have left off in the previous video with regards to this de Moivre's theorem, and this will be a part 2 video. As you remember previously, I discussed the powers of complex numbers. Today the main focus of this video are the roots of complex numbers. It's going to be slightly more complicated of a topic than was that previous video which focused on the powers. But before we actually delve into the subject on roots, I want to do one review example with regard to the powers of complex numbers. You know, complex numbers are in the form z is equal to x plus iy. That's the form of complex numbers. It's not a difficult form, and we also know that to determine the complex numbers we have to use a formula where z to the power of n, the power of a complex number is equal to the modulus to that same number. Then you do cosine n theta plus I sine n theta. You have to run your complex number through this equation with regards to the form that you are dealing with. So if you have an example which looks something like this, you have to determine 2 plus 3i, this sixth power of this complex number. The first thing you need to do is determine the polar or the trigonometric form of this complex number, and you can do that easily by doing a quick graph to orient you with regards to where you are. You have 2 across, 3 up, and the modulus of course is equal to the square root of the sum of these individual components square. You get a root 13, and your angle theta, which is your direction with regards to this line, the modulus is always the inverse tangent of y over x. Our y component over here is really a 3. 3 divided by 2 is a 1.5. You inverse tan 1.5, and you get a very good answer of 56.3 degrees. 56.3 degrees. Then you can easily write this into a complex form, where your complex form is equal to root 13. And this complex form is also, I'm talking about here, the polar or the trigonometric form, cosine 56.3 plus I sine 56.3. Now when we have to determine this complex number to the power of 6, all we gotta do is bring in a couple of 6's over here. And then of course we need to bring an n over here. We know we're gonna bring a 6 coefficient over here and a 6 coefficient over here. We're gonna solve this all out. So root 13 to the power of 6 can be viewed as very easily using the laws of exponents as 13 to the power of 1 or 2, which is the square root of 13, all to the power of 6. Right? All to the power of 6, which is the same thing as saying 13 to the power of 6 over 2, which is the same thing as saying 13 to the power of 3, which, as you know, with your handy dandy calculator, you do 13 to the power of 3, you get a 2197. So this right here is your modulus to the power of 6, 2197. Now the rest is all calculator work. You have to do 56.3 times 6 and cosine of that. 56.3 times 6. Remember, it's always n theta and n theta. So you get 337.8 degrees as your angle. You cosine that, you get a 0.9258. And then we can do the same thing over here. 56.3 times 6 sine of that value, you get a minus 0.3778i. Now all you do is when you open up this parentheses, you get a very good answer, and that's your final answer actually. So we do 2197 multiplied by this value right here, 0.9258. We get a 2033.9. Let's just round it up, 2034. We could have been off by 1 or 2 digits simply because of the decimal places we're using. And then over here, what do we get for our second component? We get 0.3778 minus times 2197, and we get a minus 830i. Again, we can be off by 1 or 2 digits simply because of the decimal placements. But this right here is an answer, 2034 minus 830i. And this right here represents this complex number to the power of 6. Not a difficult question. So just remember this formula over here. This is the formula for determining the powers of complex numbers. Next we'll be looking at the roots of the complex numbers. It will be slightly more involved of a formula and slightly more involved of a use of that formula in terms of the questions that you will see. So when it comes to the determination of the complex roots of these complex numbers, you have to look at the formula right over here. You can see it's slightly more involved. If this represents your polar form of your complex number, or cosine theta plus I sine theta, and you know how you can derive that from a set of complex coordinates using the complex plane, determining the modulus and the argument. You can derive this formula. Then from here you have to actually convert it or use this aspect and run it through this formula. Basically the nth root of any complex number is always equal to the nth root of your modulus, and in this large parentheses you have to do this. You take the cosine of the theta plus 2 pi k. K represents which root number you're looking at, all divided by n. Of course the n over here and the n over here are exactly the same values. The main value over here to focus on is this k value. K value is basically going to be this. You'll always start out with regards to the number of roots you have to determine, and then you'll go next to the next value 1 and 2 and then 3 until you're done, however long it may take until you are actually done with the question. If supposedly a question set for a specific complex number, you have to find the fourth roots. You know you're going to start again from 0, but you have to do a total n value here of 4. N value here is a 4, so you're going to do 0, 1, 2, 3. Remember n minus 1, 4 minus 1, you'll get a 3 over here. But you'll look for 4 different roots, but you'll start from 0 and you'll always end at n minus 1. If the question was to find the 6th roots of a complex number, you know n minus 1 over here is going to be 5. 6 minus 1 is 5. So you'll do 0 will be your first one, k value of 0, then 1, then 2, all the way up to 5. You'll still get your 6 different roots because you're finding the 6th roots, but you'll start from 0 and you'll always end at n minus 1. These numbers over here are representative of your k values. You'll always start with the k value of 0 and you run it across using this formula. Then you'll do the next k value and run it across till however many required roots are there for your question, and then you'll end. So keep this this process over here in mind. Everything over here is actually pretty easy. The complication sometimes arises in determining the root of your complex number modulus, and also without spoiling the application of the k value over here. What are your indexes here is for your radical is always the denominator here, and this n and that n are the same, and you got to run these things through. You have the process of writing your form, your final complex forms, root forms in their unsimplified form, or you can take them on into their decimal, the completed simplified form. There's always the option, if you want, you can graph them out. You don't have to graph them out. If you can derive all of these solutions, that in my opinion is more than enough. Let's look at some examples using this formula for the determination of complex roots. So let's look at the board over here. We have the formula written out over here. This is the formula we'll use for our complex number. Once we have determined the complex number, questions can give you the coordinates and you have to determine the trigonometric form, the polar form of that complex number, then go from there. Or you can already have everything provided to you and you just run it through the formula. Our question is this: you have to determine the 6th roots of 1. And you know, if you're talking about 1, we're looking at a complex number which looks like this. 1 plus 0i is equal to 1. And you know, if you graph 1 comma 0, you're looking right over here at 1 comma 0. You know very clearly and easily that your modulus is equal to 1 and your angle is equal to 0 degrees. So let's quickly write using this into the trigonometric form. Our complex number is really going to be 1 cosine 0 plus I sine 0. That's my trigonometric form, or the polar form. Now I have established this form and we have to run it through here. And you can remember very clearly this k value is going to be your rundown always from 0 up to n minus 1. What's my n value over here? It's 6. 6 minus 1 is going to be 5. So we're going to start from 0 and we're going to go up to 5. You'll still get 0, 1, 2, 3, 4, 5, 6 different roots, but you'll be starting from 0 and you'll be ending at 5. So the procedure for this question is going to run something like this. Your very first root, which you're going to identify with k value of 0, is going to be this. And you know your r value here is 1, and you got to do 1 to the 6th root. 1 to the 6th root, of course, is just going to be a 1. See, the 6th root of 1 is just equal to 1. So in terms of just cleanliness, we'll be putting our value over here just as 1. Then we're going to put everything in, we're going to plug it in. We have cosine theta, which is 0. Our theta is 0 over here, plus 2 pi times k value here of a 0, all divided by 6, plus I sine 0 plus 2 pi times k value here 0 all over 6. Right here, over 6. That's my first part. Now my next one, remember we have to go all the way up to 6 different roots. The next sequence of events will be 0 plus 2 pi times 1. Now the k value is 1. All divided by still the n, which is still a 6, plus I sine 0 plus 2 pi to the power of 1, not to the power of 1 times 1, which is your k value, divided by 6. My second one, of course, is going to be 1 times cosine 0 plus 2 pi. Now we have a 2 over here. K value is a 2. These are your k values. Divided by 6 plus I sine 0 plus 2 pi times 2 over 6. Now we're going to run into a little bit of a space issue, aren't we? Let's keep going as far as we can. And then we have 1 over here. We have cosine 0 plus 2 pi, k value here is of a 3 divided by 6, which is my n, right here, my n, 6, plus I sine 0 plus 2 pi times 3, the k value, divided by 6. Let's squeeze one more over here. We have to go up to 5, but let's squeeze a number 4 over here. 4 will be 1 times cosine. You can see this is a process, isn't it? 0, which is my theta angle, plus 2 pi times 4, my k value, divided by 6, plus I sine 0 plus 2 pi times 4, my k value, all over 3. And then let's close it up. We have to squeeze in the fifth one somewhere, and where should we do that? Let's squeeze it over here. We'll write it small, but we'll squeeze it here. My fifth term of these 6 roots will be 1 times cosine. Remember, this is this part right here. Nth root of r. 6th root of 1 is 1. Cosine 0 plus 2 pi times 5 over 6 plus I sine 0 plus 2 pi times 5 over 6. Now we actually have the fun process of solving all of these out, which is not necessarily hard. Let's look over here. 2 pi times 0 is a 0, and you just end up with a 0 divided by 6, which is just a 0. Cosine of 0 is just a 1. Look over here. 360 times 0 is 0 plus 0 divided by 6. This is all 0. So we just end up with a 1 over here as our very first term. Not hard. Now look over here. We have a 2 pi over 6. 2 pi times 1 over 6. And 0 plus 2 pi over 6. We're basically ending up here with a pi over 3, which is 60 degrees. Cosine of 60, if you remember using your trigonometric ratios, is a 1 over 2, and sine of that same 60, whatever angle you determine here is the same over here. Sine of 60 will be plus I root 3 over 2. Remember those trigonometric ratios. Now look over here. You have 2 pi times 2, which is a 4 pi over 6. If you simplify 4 pi over 6, these zeros are all meaningless. 4 pi over 6 is the same thing as saying 2 pi over 3, which is 120. Cosine of 120 is a minus 1 over 2. But sine of 120 is positive I root 3 over 2. Now look over here. 2 pi times 3 is a 6 pi divided by 6 is a pi. All of this is just a pi, 180 degrees. Cosine times 180 is a minus 1. Sine of 180 is a 0. You don't have any term over there. Now let's come down over here. 2 pi times 4 is an 8 pi over 6, which is a 4 pi over 3, which is a 240. Cosine of 240 is a minus 1 over 2. And sine of 240 is a minus root 3 over 2, and then you have to put the I over here. The last one over here, number 5. 2 pi times 5 is a 10 pi. 10 pi divided by 6 is a 5 pi over 3, which is 300. Cosine of 300 is going to be a 1 over 2. And sine of the 300 is going to be minus root 3 over 2, but you have to do minus I root 3 over 2. And now you have determined all of these 6 roots. 1 and this, and this. You can convert these all into decimal answers if you want, or you can leave these answers as is. So here are my 6 roots of this complex number right over here. These are my 6 roots. An elaborate process. The 6 roots of the number 1, which is in itself a complex number, because this complex number, it looks like 1 plus 0i. In the polar form, it looks like this. But this right here are the 6 roots of this complex number. So you can see how the process runs through. We basically need to keep doing some more examples to understand this process better. So here's a second example. We have to find the cube roots of this complex number. You can't do much with this complex number until you convert it into the polar form. For this question, you have to convert this into the polar form. And the best way you can do, as always, proceed through a complex plane to visualize where it exists. It'll be right here, -2 this way, 2 this way, and a second quadrant angle. Your modulus, of course, is going to be 2 root 2, which is the same thing as root 8. You can do 2 squared plus 2 squared, square root of that is root 8, 2 root 2. Theta is, of course, going to be inverse tan of your y value divided by x value. It will be a inverse tan of a -1, which will be a minus pi over 4. And you know minus pi over 4 in the second quadrant is 135 degrees, 135 degree angle. Or you can just say 3 pi over 4. We have everything now we need to write this in the trigonometric form. Our trigonometric form for this number will be 2 root 2 cosine 135 plus I sine 135. That's my polar or trigonometric form. Now that we've determined this, we should be smart this time and make space for the actual process of this question, so we don't run out of space this time. We have to determine the cube roots. So basically we want to start first by determining this nth root of this r. We know r is basically 2 root 2, but we have to determine all of this in terms of the cube root. You know, the cube root, we have to get a single good value of r, which we'll plug in through that formula for this area right here. So you want to look at this in two ways. You want to look at it by opening it up using the powers, exponential rules and the radical rules. You get 2 to the power 1 or 3 times 2 to the power of 1 over 2 times 1 over 3. You see this radical 2 to the root 2 is same thing as 2 to the 1 over 2. Then you're still opening it up with the 1 over 3. So you basically get 2 to the power of 1 over 3 times 2 to the power of 1 over 6. Now you basically just have to add these. 1 over 3 plus 1 over 6 gives you what? 1 over 3 plus 1 over 6 based on the law of exponents is 1 over 2. So you basically, the cube root of 2 root 2 is equal to root 2. This right here is going to represent this value right here, root 2. So we got everything we need now to start doing the actual question. We have root 2. So remember this, root 2 represents this value over here. So by k term 0, it'll be root 2. And then we know we're going to start running it through. My theta angle, of course, was 135. 135 plus 2 pi times 0. Remember, it's always 2 pi k. Here k is 0. All divided by your n value, which is your right here, your cube, which is a 3, plus I sine 135 plus 2 pi times 0 all over 3. And my next k value, remember k values are 0 all the way up to n minus 1. My n is 3, n minus 1 is a 2, so we'll do 0, 1 and 2 and that'll be it. This part will run through like this, 135 plus 2 pi times 1, k value of 1, divided by 3 plus I sine 135 plus 2 pi times 1 over 3, right, over 3, last k value, because it's n minus 1, 3 minus 1 is 2, so we'll end up at 2 root 2 cosine 135 plus 2 pi times 2 over 3 plus I sine 135 plus 2 pi times 2 over 3. Now for this question over here, I'm going to present a decimal answer because I feel like doing a decimal answer. Now the way I'm going to do the decimal answer is this. I'm going to take root 2 and I'm going to save these values in my memory recall. I'll do square root of 2 and I'll save them. Then I'll individually do each of these and multiply them. Let's look over here. It's 135 divided by 3 because this 2 pi times 0 is meaningless. It's 0. 135 divided by 3. 135 divided by 3, I get 45 degrees. 45 cosine times my saved value, I get a value over here of 1. Now let's do the same thing for the sine. 135 divided by 3 sine of 45 is 1 over root 2. 1 over root 2 times this, you'll get a plus 1i. Or you can just say a plus i. That's my... Now I know I said decimal answers, but 1 is still a decimal answer, it's just 1.0. Let's look over here. 135 plus 360. 135 plus 360 divided by 3, I get 165. Cosine that, multiply that by memory recall, I get a minus 1.366. Minus 1.366. Let's do this one right over here. 135 plus 360, remember 2 pi times 1 is 360. divided by 3, I get 165 degrees here, sine that and multiply that by root 2, I get a 0.366i plus 0.366i. There's nothing wrong with presenting decimal answers. Absolutely nothing wrong with that. Now let's look over here. We have 360 times 2, which is 720, plus that from 135, and divided by 3, I get a value here of 285. Cosine that and multiply that by your memory recall, you get a 0.366. 0.366. If you were to graph these out, they will give you very symmetrical results, but we're not going to be graphing things out today. Let's look over here. 135 plus 720 divided by 3, sine that, multiply that by your memory recall value, you get minus 1.366. Minus 1.366i. So those are our 3 roots or cube roots of this complex number right here. Minus 2 plus 2i. It's a complex number but not in the polar form. But these are our answers over here. More examples coming up. This next question shouldn't be too hard. We just have to determine the complex roots of minus 25i. But we have to determine the square roots. You know the square by default means 2, right? We're looking here at an n value of 2, right? So in terms of the k values, you're going to start from 0 all the way up to n minus 1. So you're going to start from 0 and then you'll just do n minus 1, 2 minus 1 is a 1. You'll just have 2 roots, 0 and 1. These will be your square roots of this complex number. But we have to understand what this complex number is. Minus 25i is the same thing as viewing it as the real number component minus the imaginary number component. Remember x plus yi, real number minus real number and imaginary component. You can view this as a coordinate 0 comma minus 25. And you know when you graph it out, you end up with a minus 25 over here. Your r value is of course 25. Your theta value over here is on the negative y-axis line, which is 270 degrees, 3 pi over 2. So our trigonometric form of this complex number will be r value of 25 times cosine of, let's keep this in the radian form, plus I sine 3 pi over 2. So this whole number has been deciphered into that trigonometric form. As you know, everything with complex numbers is usually complicated because it's a process. But the process is easy. Sometimes it can be a little tricky, but this process over here is easy. Now let's actually determine our roots. Our roots over here are going to be 0 identified with the k values of 0 and 1. And you know we have to do the nth root of this modulus. The square root of this modulus, 25, is going to be just a 5. So we get lucky over here with an easy number. Then you do cosine of theta, which is 3 pi over 2 plus 2 pi times k value here, which is a 0, all divided by n, which is a 2. Do that the same for the sine component, 3 pi over 2 plus 2 pi times 0 all over 2. Remember, n values are 2. My n value is 2, which corresponds to the square. Let's do the k value of 1. Cosine 3 pi over 2 plus 2 pi times 1 all over 2 plus I sine 3 pi over 2. I should probably change this marker and I'll do it for the next question, divided by 2. And now all we have to do is the wonderful process of solving this out. It shouldn't be hard. So let's actually open this up. Let's look over here. So we have 270 and we're going to divide that by 2 because this over here zeroes out. 270 divided by 2, we get 135. Now you do the cosine of that. Cosine of that. And we can do minus 0.707. Actually for this one, I'm going to present non-decimal answers. I know this is minus 1 over root 2, which is cosine of 135. So I'll get a minus 5 over root 2 as my real part of this root. Let's look over here. 270 divided by 2 is 135. Sine of that is going to be a positive because sine is positive in the second quadrant. I'll have plus 5i over root 2. That's the first part. Now let's do the second root. We'll do 3 pi over 2 plus 360 divided by 2. 270 plus 360 divided by 2. I'm getting a 315. A fourth quadrant 45 degree angle. 315. Cosine of that will be 1 over root 2. 1 over root 2. So you'll get a 5 over root 2 over here. And you know you have a 315 here because what this angle is the same as this angle. Sine in the fourth quadrant 315 is a minus angle. So you're going to have a minus 5i over root 2. These 5's of course are coming from the opening of this parentheses. 5 multiplies with everything on the top, and the denominators are your 45 degree over root 2's being generated that way. So this right here should be your final answer. You should have 5 minus 5 over root 2 plus 5i over root 2, and then 5 over root 2 minus 5i over root 2. These are the two complex root answers for the square roots of minus 25i. Not a difficult question, but still a process was involved over here. You could have generated this into a decimal answer, but I didn't. So for this question, we have to determine the fifth roots of 128 times minus 1 plus I. You have a little bit of a change over here because you have a 128 coefficient of this complex number over here, which is fine. Look over here in this parentheses part and use that as your complex number for derivation of the trigonometric form. You really have a minus 1 comma 1. And in terms of graphing, minus 1 comma 1 would be right over here. Minus 1 and 1. You know the r value would be root 2, 1 square plus 1 square square root, and the theta will be inverse tan of a minus 1, which is a minus 45 degrees. Minus 45 degrees in a second quadrant angle will be 135 degrees. So we basically have our complex number written over here. Our complex number is going to be this. You'll have root 2 times cosine of 135 plus I sine of 135. But let's not forget about this 128 over here. Let's create some space over here and let's deal with that 128 coefficient. So our complex number here has been determined to be root 2, but our complex number really is 128 root 2, because 128 is like in a multiplicative aspect to this complex number. But we have to determine the fifth roots of all of these, don't we? We have to determine the fifth roots of all of this. Look what I'm doing over here. I'm making it look like this. Now we have to actually do something over here, because when we actually run this down to the formula of the roots, right, for those k values, we need to have a good value over here for our r. So 128 is really 2 to the power of 7. And then we have root 2. You can bring out 2 to the power of 7, because 2 to the power of 7, you can view it as this. 2 to the power of 5 times 2 to the power of square times root 2. Look over here, I've separated 2 to the power of 7 into two components, 2 to the power of 5 and 2 to the power of square. 2 to the power of 5 can come out as a fifth root, as just a plain 2. And what are you left with? 2 square root 2, which is 4 root 2. This over here will represent your value, which you'll be putting right over here. That will be your value. Let's put that over here so I don't forget that. It will be 2 fifth root of 4 root 2. That will be my modulus value with the fifth root applied to it. Now let's look individually at our k's, at our individual roots. Let's do that. We know k value will go always from 0 to n minus 1. N minus 1 will be here, 5 minus 1, 4. So we'll go from 0, 1, 2, 3, 4. That's what we'll do over here. So we'll have 5 individual roots, but we'll start from 0, k value of 0, and then we'll work it down to a k value of 4. So let's do that. 0. We'll have 135 degrees as my, let's keep everything here in the degree format and let's not convert it to radians. My this value over here is 2 to the fifth root of 4 root 2, and then we do cosine of 135 plus 2 pi times 0, because k value here is 0, all divided by 5, n is a 5, plus I sine 135 plus 2 pi times 0, all divided by 5. You seeing that? Look at my next k value. These are my k's. 2 to the fifth root 4 root 2 cosine 135 plus 2 pi times the k value of 1, because k value here is a 1, so you put a 1 over here, always divided by the n, plus I sine 135 plus 2 pi times 1, all over the n value, which is a 5. Let's go to the number 2. Remember, we're doing 0, 1, 2, 3, and 4. 2 to the fifth root of 4 root 2 times cosine of 135 plus 2 pi times 2 over 5. It can get sloppy, it can get messy, it can get tiresome. It can become a whole bunch of things actually. Divided by 5. Let's do the number 3 k term. These are basically just the term, the k term root, the 0 term root, the first term root, the second term root, the third term root of the complex number. You'll do 2 fifth root 4 root 2, and then you do cosine 135 plus 2 pi times the k value here of 3 over 5 plus I sine 135 plus 2 pi times 3 over 5. See, it can get sloppy basically. 4 root 2, then you do cosine 135 plus 2 pi times k here is 4. It's basically so much easier when you're doing it on a paper because you have better command of everything. 135 plus 2 pi times the k value. Why am I writing k? I need to put actually a number over here. My k value over here is a 4. All divided by 5. And this right here is the rundown of this entire question using this polar trigonometric form. Let's clean this out for neatness sake because it will just look so much better that way. Let's look over here. We're going to have to solve this out. So now we actually have the tedious aspect of solving this out. The first thing you want to do is solve this out right over here and save this into your memory, and then you can keep recalling this memory and multiplying it. And the procedure for this is to work from inside and work outwards. Look at 4 root 2. Do square root of 2 multiplied by 4, and this product over here is going to be to the 5th root. And you want to do that to the 5th root and multiply that by 2, and you get a value 2.828, 2.82. And the button you're basically looking at on your calculator is this one right over here, x to the y, and then on the top you have x to the power of 1 over y, which you will use with the shift function. X to the power of 1 over y, you put your value and you do shift and hit this button, hit 5, you'll get your 5th root. So keep this button in mind. Now you have to look individually, and I've saved this value here. Now you have to look individually at each of these steps. You do 135 divided by 5, and you cosine it and you multiply that by your memory recall, you get a 2.52 over here. And remember, this of course is tedious process. That's just how it is. And look over here, 135 divided by 5, and you sine that and you multiply that by your memory recall, you get 1.28i plus 1.28i. Now you can individually do that through all of these. 135 plus 360 divided by 5, 135 plus 720 divided by 5, and keep running them down, and you'll get a bunch of answers. For the interest of time, I've actually had these answers worked out, and I'm just going to put them down over here. This way I'm not going to spend the next 4 minutes of your time just calculating everything out, but your answers will be these, and I'm going to put them out over here. Minus 0.44 plus 2.79i, and the next one will be minus 2.79 plus 0.44i. Depending on where these angles, in which quadrants they happen, these are still second quadrant, these are still first quadrant. You can just tell clearly by the signs over here. Sign is always positive in the second quadrant. Now we'll end up in the third quadrant over here. We have a minus 1.28, minus 2.52i, and your last one is going to be in the fourth quadrant, 2 minus 2i. So these are your answers over here. So you have the answers now in front of you. You can run these out through yourselves and compare them to what I have on board and make sure that you have the right answer. I think the most difficult part of this, some of these questions, is determining this value over here, which is this over here. Sometimes that can be very tricky because this part over here is mundane. You're just running it through the formula. That's not hard. Determining this component sometimes can be very hard. Let's look at another example. Now here's a question, x to the power of 4 minus I equals 0, and your question can always be presented in this form. You have to determine the fourth roots of this complex number, the fourth roots. Okay, and how do you know it's the fourth roots? Because you're basically looking at this exponents to the power of 4. Look, if you solve this out, x to the power of 4 is equal to I, x is equal to the fourth root of I, so you're determining the fourth root of I. But you have to first convert this into your trigonometric form, and you know the trigonometric form, if you just look over here, x to the power of 4 is equal to I is really saying 0 plus I, which is really saying is 0 comma 1. So you're really looking at that, a 0 comma I or a 0 comma 1 polar form has to be generated from this complex plane, a polar form. You know the R value here is going to be a 1, the theta is going to be pi over 2 or 90 degrees because it's on the positive y-axis. Your trigonometric form of this number will be 1 cosine 90 plus I sine 90. Alright, so you can see sometimes the question can be worded in an equation form, and you have to first be able to convert that into your complex plane form, and then of course from there you can determine your polar form. So now we have to determine the roots. We know n here is 4, so n minus 1 is 3, so we're going to start with k value of 0, 1, 2 and 3. We'll get our 4 roots. So 0, 1, 2 and 3 will be our headings for those 4 roots. So let's actually do those. It shouldn't be a hard question. We'll start with the first k value of 0. And am I missing anything over here? We know our modulus here is a 1. The 4th root of 1 is just a 1, so that's easy. The 4th root of 1 is just a 1. So we have a very easy modulus here in terms of the root. You'll do cosine of 90 plus 2 pi times k value of 0 over 4. And here is a 4. Plus I sine 90 plus 2 pi 0 over 4. And let's do the next one, the next term, the next root. Cosine 90 plus 2 pi times the k value of 1 over 4. It's really not hard, but it is tedious. 2 pi times 1 over 4. And then number 2, the third term, but number 2 in terms of k, 1 times cosine 90 plus 2 pi times 2 over 4, your n value, plus I sine 90 plus 2 pi times 2 over 4. Hopefully my handwriting is not getting too sloppy over here. It might be, but I hope it isn't. 1, this is my last term, k value of 3, n minus 1, 4 minus 1, 3. Cosine 90 plus 2 pi times the k value 3 over 4 plus I sine 90 plus 2 pi times 3 over 4, and we have everything laid out. Now we have well, you can say it's a fun task of actually calculating it out. Let's actually view it as a fun task and do it, because these values are here all 1. We have a 90 plus 0 divided by 4, so we have a 90 divided by 4. Cosine of 22.5. I get a 0.9238. 0.9238. And then I have a sine of the same value, 90 divided by 4, sine it, plus 0.382i. I'm not taking these to too many decimal places because I'm feeling lazy to do so. Let's look at this next one, 90 plus 360. 90 plus 360 divided by 4, I get 112.5. Cosine of that, I get a minus 0.382. And let's look over here. Sine, I get a plus 0.9238i. Let's look at this next term. 90 plus 360 times 2, 360 times 2 plus 90 divided by 4, I get a 202.5. 202.5 cosine is a minus 0.923, and we know we're going to be in the third quadrant, we'll have a minus over here. Let's do sine of that, we get a minus 0.3828i. Last, it'll probably put us in the fourth quadrant. 90 plus 360 times 3 divided by 4, I get a 292.5 over here. Cosine of that, I get a 0.382, and the sine of the same value, I get a minus 0.9238i. Hopefully handwriting was relatively readable here, but the answers are laid out. The complex roots of this number, which is really, as I showed you, 0 plus I of this complex form, are these roots laid out in front of you. How about this question? X to the power of 5 plus 243 equals 0. We have to determine the roots of this system over here, and of course you have to convert this into some complex number. The process you're going to do is this: x to the 5 is equal to minus 243. This right here will give you the clue to what you're looking at. You're looking at something which looks like this. This should be a 243 minus 243 plus 0i. Remember, z is always equal to x plus yi. Your real number and your imaginary number component. Here's my real number, here's my imaginary number. If you're looking at this in this way, minus 243 comma 0, or minus 243 plus 0i, it clues you in to exactly where you are, right over here. You have an r value, a modulus of 243. this square plus this square root is going to be 243. It's not minus 243, it's going to be positive 243. And you know your angle over here on the minus x-axis is pi or 180 degrees, right? You know what we got as our complex number is going to be 243 cosine of pi plus I sine pi. My polar or trigonometric form has been determined now. We have to determine what type of root. We have to determine the fifth roots because the power of 5 clues you in. We have to determine the fifth roots. The fifth roots are, of course, n is equal to 5. N is equal to 5. And we have to determine that, the 5 roots. Now for the sake of this video, as being more of an instructional basis, I'm just going to lay it out in terms of the formula part, but we won't actually calculate the finalized answers because that's just the calculator part which you can do on your own. So let's do that. So we're determining only the fifth roots of this because it's x to the power of 5 plus 243 equals 0. We have to determine the 5 roots, the complex roots. And you know it's always k is always from 0 up to n minus 1. What's my n minus 1? It's 5 minus 1, it's 4. So we're going to go from 0, 1, 2, 3 and we'll stop at 4. 0, 1, 2, 3 and 4. And what's going to be my this value over here, right here? Well, it's 243, but to the fifth root. What's fifth root of 243? I believe that would be a 3. But let's see. You do 243 and you look for that button I told you, and you hit 5, shift and 5, and you get 3. And remember, the button I'm talking about is this. X to the power of 1 or x to the power of 1 over y on your calculator. This is the function you're using, and it's usually a shift in inverse to get to this function. So look, keep your eyes out for that button. Anyhow, my r root, the modulus root, is 3. And let's fill out everything else. Cosine theta is pi plus 0, 2 pi times 0 over 5 plus I sine pi. Now I'm getting a little sloppy here. Plus 2 pi times 0 over 5. That's my first one. Let's look at my next one. Cosine pi plus 2 pi times 1 over 5 plus I sine pi plus 2 pi times the k value here, which is a 1, over 5, which is my n value. And you know what this will be. Cosine of pi plus 2 pi times 2 over 5. And remember, you can calculate all of this out on your calculator, what your final answer will be. I won't be doing that. And the fourth one, which is number 3, but the fourth term, the fourth root, cosine pi plus 2 pi times 3 over 5 plus I sine pi plus 2 pi times 3 over 5. And my last term, 3 times cosine. Everything is by multiples of pi over here, as you can see. 2 pi times the k value of 4 divided by 5 plus I sine pi plus 2 pi times 4, the k value, divided by the n value of 5. And of course you can calculate all of these out, but everything has been laid out to you. Just for curiosity's sake, what are we looking at actually over here? Pi divided by 5. 180 divided by 5 is 36 degrees. Let's look at 180 plus 360 divided by 5, 108 minus 36. We're looking at multiples of 72 over here. So actually let's look, we're not going to solve this out, but we're going to look at this. We're getting a pi plus 2 pi times 0 over 5. We'll be getting a pi over 5 as our value, which will be hit by the functions, the trigonometric functions. Here we're getting a pi plus 2 pi, 3 pi over 5 as our factor, which will be hit by the functions. Pi plus 4 pi is a 5 pi divided by 5. We're getting a pi over here. Pi plus 6 pi, 7 pi over 5. And then pi plus 8 pi will be 9 pi over 5. Let's just look at what these values will be in terms of their angles. Pi over 5, 180 divided by 5 is 36 degrees. This will be 36 degrees, which you'll run through your function. And then 3 times 180 divided by 5, this will be 108 degrees. Okay, 108 minus 36 is a 72. And then of course this right here is 180. And let's look at 7 times 180 divided by 5. I'm getting a 252, which of course is 180 plus 72. So we are going here by multiples of 72. 9 times 180 divided by 5, 324 degrees. So everything over here is by multiples of 72. Anyhow, you can solve this out for yourself and see what the final answer is. I'll present one more question and that'll be the end of this video. But you can see that this video, it can be a little messy, it can be a little tedious, the whole process is a little more involved, but it's not hard, it's just more involved, and everything runs out through this formula. So as our last question, we have to determine the cube roots of this complex number, root 5 minus 4i, and you know root 5 over here is your x component or your real component, and here the minus 4i is of course your imaginary component. It would be root 5 comma minus 4. If you plot them out, root 5 comma minus 4 puts you in the fourth quadrant, and you will be minus 4 down this way, and you'll be root 5 across that way. And you know the modulus, I was going to say the radius, the modulus here is going to be root 5 square plus minus 4 square, and you'll square root that, you'll get 5 plus 16, you get a root 21. And your angle of course is the arctan of the y component divided by the x component, minus 4 divided by root of 5. 4 minus divided by root of 5, and inverse tan, I get a minus 61 degrees. But you're in the fourth quadrant, you got to add that to the 360 to get a proper angle. Your proper angle is 299 degrees. 299 degrees, because you can't be looking at minus 61 or whatever that number was. You have to adjust it with regards to your reference horizontal. So your complex number is going to be root 21 cosine of 299 plus I sine of 299. This is what you're going to use to determine your cube roots. Your polar form will be used in that formula to determine your cube roots. Should not be a hard question, should be an easy question. Now our first task is to determine this part over here. We know root 21 has to be done in terms of the cube roots. We know root 21 is the same thing as saying 21 to the power of 1 or 2, but we have to determine the cube root of this, right, don't we? To the power of 1 or 3. So we really have 21 to the power of 1 or 6, which is really 6th root of 21. That's what our term is over here. So do not make the term of looking at root 21 over here and then just putting a 3 over here and just transporting this over here and saying that this is your term, your modulus term, but that's not going to be right. Our first term, we have to do cube roots, 3 different terms. First term will be 6 root 21. We'll do cosine 299 plus 2 pi times the k value 0 divided by 3 plus I sine 299 plus 2 pi times 0 all over 3. Our next term, number 1 term, k value number 1 will be 6 root of 21 times cosine 299 plus 2 pi times 1 over 3 plus I sine 299 plus 2 pi times 1 over 3. And our last term, which is k value of 2 n minus 1, is 6 root of 21 times cosine 299 plus 2 pi times 2, the k value, divided by n, which is 3, plus I sine 299 plus 2 pi times 2 over 3. We're not actually going to solve this out because you can do that by a calculator, you can do all of that. I'm just curious to see what these angles will be which would have been affected by these functions. The first angle relating to the k term of 0 would be 299 divided by 3. 299 divided by 3, which would be 99.6. The second term would have been 299 plus 360. 299 plus 360 divided by 3, I get a 219.6. And the third angle, which would be derived from this part and this part, would be 299 plus 720 divided by 3, 339.6. So each of these is like 120 degrees away from the next number. This over here is 120 degrees away, this from here is 120 degrees away. Everything is always usually symmetrical with these complex numbers, especially if you were to graph them out. I'm talking about these roots of complex numbers generate very symmetrical or very nice graphs if you were to graph them out. So I'm not going to actually solve all of this out. You can do that. You have the angles written over here. These are the same angles, 99.6, 219.6, 339.6. Multiply that out by this. You can run this on your calculator. Just do 21 and you'll do the 6th root of that. by looking at this function on your calculator, which looks like this, x to the power of y, and there's a little thing over here, x to the power of 1 over y. You have to do shift inverse to activate this top function, and you'll do 21. You'll do shift inverse that button, and you hit 6, and you'll get 1.66. So 6 root of 21 will be 1.66. It's the same thing as saying 1.66 times 1.66 times 1.66. 6 times you'll get 21. But you can run this out and you can calculate out the specific roots, but the process is laid out in front of you. I hope you all enjoyed this video. I know it's not an easy video. I know it was a little bit messy and it was a little tedious, and maybe the board ran out of space in some areas, or you have a little bit of dark shadow over here. But I hope at the end of the day, when you look at the video, you'll be able to understand this concept of the roots of the complex number. Remember, the powers of complex numbers and the roots of complex number are all part of that DM theorem, the de Moivre theorem. So keep all of these things in mind. The whole concept of complex numbers is not bad at all. It's actually pretty interesting. It's a little difficult, but it's interesting. Please like, subscribe, and share. Thank you for watching and have a nice day. Bye.